Hi, my name is Thomas Kim. In this session of video, I am going to develop algorithm for Diophantine equation. Diophantine equation is used to find the decryption key in RSA algorithm. Diophantine equation is of this form: ax plus by equals k, where k is evenly divisible by GCD, greatest common divisor of a and b. K should be evenly divisible by greatest common divisor of a and b. Then we can solve this Diophantine equation. It is used to find decryption key in RSA algorithm. One of my subscribers wrote me like this message: very precise and up to the point video, but such complex topics sometimes you need to be a bit descriptive. By Mr. Ajit Gupta. He is one of my subscribers, and he wrote this message. He wanted me to give somewhat descriptions about my videos at the beginning, at the start of the video, so I explained it. And in this, to implement Diophantine equation, in my case, I refer to DLBmaths, Mr. DLBmaths YouTube videos, and also Professor Jeff Suzuki's YouTube video I watched quite a lot, and his YouTube video was really great. And also I watched Mr. Glenn Olson's YouTube videos. All these YouTube videos about Diophantine equation was quite useful. Among them, DLBmaths, Mr. DLBmaths YouTube video was most helpful, but Jeff Suzuki's and Glenn Olson's YouTube video also was a lot helpful to understand Diophantine equation. Thank you very much, Mr. Ajit Gupta. I am not sure how to pronounce your name properly, but your comment meant really a lot to me. Thank you. Okay, so we are going to solve 7x plus 13y equals 1. The very first step we have to do is, if this k is divisible by GCD, greatest common divisor over 7 and 13. So the very first step is we have to get GCD of A and B, in this case 7 and 13. And second, K, in this case 1 should be divisible by G, in this case 1. And K is 1 should be divisible by G, means remainder K divided by G, remainder should be 0 in fact. So since this satisfies all criteria, this condition, we can now solve it. So first, in case A should be always greater than B. In this case, we have to swap them. So it should be 13y plus 7x equals 1. We have to start like this way. So the second condition will be, about this I will talk later again. Now we are solving it. For example, 13 equals 7 times 1 plus 6, like this. This is basically, I'm using Euclidean algorithm here. Now we move, this is A, this is B. We bring B to here, 7 equals, and remainder R comes here, 6 times 1, remainder 1, like this. And we bring 6 here, B again, 6 here again, 6, and remainder here, 6. Now, no, here the remainder is 0. So we completed Euclidean algorithm. Now I delete Then we underbar like this. Underbar. We regard all underbarred items as variables. We move this term on the left hand side like this. 13 bar minus 1 times 7 bar equals 6 bar. We moved this term to this side. We also move this term to this side like this. 7 bar minus 1 times 6 bar equals 1 bar, like this. Now we are going to replace this number to here. Instead of this number, we substitute this equation in place of 6, like this. 7 bar minus 1 times here, 13 minus 1 times 7 bar equals 1, like this. Actually, this is GCD using great Euclidean algorithm. If you haven't watched my Euclidean algorithm, please watch my previous video about Euclidean algorithm. Now we arrange the items. Please watch this. You have to compare this and these two equations. I will expand 1 times 13 plus 1 times 7 bar equals 1, like this. Now we arrange like this format. 13 should come first, minus 1 times 13 bar, then 1, then 2 times 7 bar equals 1 bar, like this. Okay. If we compare this equation and this equation, we understand this one, x0, it was minus 1. Please compare this equation with this equation, for example. Okay? This example. Then this is y0 equals 2. If we compare this with this equation, we understand that. Okay, so we bring here x0 here, x0 equal minus 1, y0 equals 2. Please note that we swapped at this stage from this equation to this equation. We swapped x and y. We have to try this equation with this value. Okay? So we put 7 minus 1 plus 13 times 2 minus 7 plus 26. This is not 1. Right? This doesn't hold. This equation doesn't hold. So we have to swap them like this. So if we swap, x0 becomes 2, y0 becomes minus 1. Okay? So if we insert this equation again, then it holds. This equation holds. Try this. 7 times 2 plus 13 times minus 1, then 14 minus 13, then 1. Okay? It holds. This step is actually very important. This step is very important. After solving the equation, you always have to check whether it holds or not. Okay? So this step is very important. So since we got x0 and x1, x0 and y0, now let's put it here again like this. 7 x0 plus 13 y0 equals 1. This is called specific solution. We want to find the general solution. How we find the general solution? To find the general solution, we can do like this. 7x0 plus 13y0 plus we multiply them. 7 times 13 7 times 13 times n, see, minus 7 times 13 times n, okay, equals 1. Because this term is 0. This term is effectively 0. We insert like this. More specifically, okay, I will do it like this. I will fix it later. This is actually not correct, but it's approximately correct. We will fix it later. Then we will arrange them with this one, this. So 7 x0 plus, I factored out 7, then it becomes 13n plus, now I factor out 13 y0 minus 7n, right, equals 1. We have this equation. So this is general solution. If we compare these two equations, this equation with this one, x is this term, y is this term. So we have another solution here. Y x equals x plus 13n y equals y naught minus 7n, like this. Please note that 13 is in case this is b actually, so we can put it like this, bn, and 7 is a, so we can say an. Okay, these are general solutions. This equation is, in this case this equation is correct, but in general case, in this case, this equation is not correct. For the time being, we will regard it as correct. So here, third step, we get 0, x naught and y naught. This is specific solution. Then we find general solution like this. General solution, x equals x naught plus bn, y equals y naught plus minus an, like this. This is temporary. We will fix it later. Please note that I binded this term with x and this certain y with this term. What about if we swap the change? What about if we do this? For example, we put it here and we bind it with this. Then it becomes like this. Like this. Is this general solution? Yes, this is general solution too. Okay? This is correctly general solution. In this case, it becomes like this. In this case, x equals x naught minus bn, y equals y naught plus an. This is perfectly correct set. This is perfectly correct set. Okay? Then why I put plus here, minus here? The reason is because in this case x naught is minus, and this term is plus, okay, plus positive number, minus positive. If we add up, then absolute value of y becomes smaller. In this case, y naught is positive, and this term is negative. This term is positive. If we subtract, then absolute value of y becomes smaller. So we want to make x and y value smaller. So that's why we put the plus symbol here, minus symbol here. We can control actually. So please note that this is perfectly valid y naught minus an. This is one set, and another set x equals x naught minus bn, y equal y naught plus an. This is also perfectly correct solutions, in fact. So, but I will erase it. Now we will try this case. Now we are solving this equation. This equation is a little bit more complex. First, we get GCD of 6 and 10. 6 and 10. It gives GCD 2 times 3, 2 times 5, and GCD is 2. So 14 is divisible by 2. K is evenly divisible by GCD. So we can solve it. So we'll have 6x plus 10y equals 2. GCD 2. We have to swap them. So it should be 10y plus 6x equals 2. We have to swap it like this. Then 10 equals 6 times 1 plus 4. And 6 equals 1 times 4 plus 2. And we apply once again. 4 equals 2 times 2 plus 0. Now we have 0. Then it becomes GCD 2, right? This is Euclidean algorithm. If you are uncertain about Euclidean algorithm, please watch my previous video about Euclidean algorithm. Here we underscore 10, 6. This is like this, 6, 4, 2. We leave a quotient like this, and we underbar every other things. Then we move this term like this on the left hand side. 10 bar minus 1 times 6 bar equals 4 bar. And we also do the same thing. We move 1 times 4 to left hand side. 6 under 6 bar minus 1 times 4 bar equals 2 bar, like this. Now we replace this term 4 bar with these equations like this, because 4 bar is the same like this. We put here 6 minus 1 times 10 bar minus 1 times 6 bar equals 2, like this. Now we rearrange this. 6 bar 1 times 10 bar plus 1 times 6 bar equals 2, like this. If we compare this equation with this equation, 10 bar should come first, minus 1 times 10 bar plus 2 times 6 bar equals 2 bar. So we let it, the first term, let it x0, we let it x naught is equal minus 1, y naught equals 2. Okay, comparing with this equation, we can let it like this. Okay, at this point we have x0, x naught minus 1, y naught 2, and we apply this value to this equation, the first equation, the second equation. Here we apply here like this. So 6 times minus 1 plus 10 times 2 equal, this is minus 6 plus 20. This is not 2. Okay, so we have to swap. If we swap them, x0 becomes 2, y0 becomes minus 1. This step is actually important. This is specific solution. Specific solution. Specific solution. Okay, we got this solution now. We want general solution. To do that, we put it here again. 6x naught plus 10y0 equals 2. Please compare this with this. This is 2, this is 14. So we have to multiply 7. We have to multiply 7 like this. Then we have 7 times 6 x0 plus 7 times 10 y0 equals 14. Okay. At this point, please watch it carefully. 7 6x0 plus 7 10 y0 plus 2 means GCD 2 over 6 times 10 times n minus 2 6 times 10 times n equal 1 equal 14. This is effectively zero. So this equation holds. Now we regroup them. We regroup with this one. We regroup, and I factor out 6. 7x0 plus 2. I factored out 6. Then I have 10n plus here I factor out 7 10y0 minus 2 6n. Okay. So I will write it here once again. Please compare this equation with this equation. Okay. So x is this term. Y is this term. Okay? This is 14. So we have x equals 7x0 plus 2 over 10n. Y equals 10y0 minus 2 6n. Okay? If we watch it carefully here, 7 is actually, no, I made it, no, this is not 7, this is 10, okay? Sorry, I made a mistake. This is 7. Okay, I made a mistake here. This is 7. Okay, so if we watch it carefully, this is k. So 7 is better like k over g. Okay, so x equals k over g x0 plus, if we watch this carefully, this is b here, b, and 2 is g. G means greatest common divisor. G over b n. Okay, y is in the same manner g over k y0 minus g over, this is a n. Okay, this is general solution. General solution. So this way I will move it to here. Okay, this equation should be fixed like this. So this is wrong. I will say 4. I will write it again. X equals g over k x0 plus g over b n. Y equals g over k x0 minus g over a n. This is general solution, so we don't need it. Now I will implement extended Euclidean algorithm. From this extended Euclidean algorithm, I will do this once again. Before I explain extended Euclidean algorithm, I will explain Euclidean algorithm in C++ code again. Euclidean algorithm is something like this. GCD, A and B equals GCD, B, A, modulo B. This is remainder. Okay, this is Euclidean algorithm. I will explain it first. The next we apply this rule repeatedly until it becomes 0. Okay, then GCD, B prime, A prime, modulo B prime. If it becomes 0, then B prime is GCD. I will implement the C++ code first. Please remember this code. It is very simple. int GCD int A int B. It's very simple. Say int R equal A. Okay, I will just say R. Now we do loop while R equals A modulo B. If remainder is not 0, A equals, please watch, B, GCD, next GCD, B is A, B of, A is previous B, okay? So A should be, this is A's place, B should assign to A, like this, B. Here, B, this, next B is, we should assign this here, so B should be in this case, this is R. See? Then done. If this is 0, if this term is 0, then it is GCD. So return B. This is simple. This is Euclidean algorithm. Very simple and elegant, lovely, right? Beautiful. Now I am explaining extended Euclidean algorithm. I will use recursive function call. For your understanding, I will also implement recursively GCD. Now, in recursively, int GCD, int A, int B. I will make it recursively now. Recursively, int R equals A modulo B. Now, we are calling this function recursively if R equals 0. If R equals 0, then B is GCD, return B. Else we return. We cannot just return, we call GCD again, GCD. This A of next GCD is B, actually B here. Then here we have to come here, R. This is recursive function call for Euclidean algorithm GCD. Now extended Euclidean algorithm. Extended Euclidean algorithm is a little bit complicated. I will use this one again here. For convenience, I will let like this. 10x plus 6y equals, for convenience, no, I will use like this. 6x plus 10y equals GCD 2. Okay? If A should be greater than B, so we swap 10y plus 6x equals 2. Here, 10 equals 6 times 1 plus 4. 6, 4 times 1 plus 2. Here, 4, 2 times 2, 0. So, we create it. Here, like this. Now we move this term here on left hand side. Then 10 bar minus 1 times 6 bar equals 4 bar, like this. Here we also move this term to left hand side. 6 bar minus 1 times 4 bar equals 2 bar, like this. Please note that this is 10 over 6, quotient of 10 over 6. Okay, this is also 6 over 4 quotient. Okay, please note that, or it is called A over B. This is also A over B, A prime, like this. Okay, so now in this place we put it here again. Before we do that, I will let it 1 like this. This is actually not 1. This should be this number. I will change it like this. Okay, before do that, I will change it. Plus, minus, like this. Plus, minus. Then it becomes like this. It becomes, I will label it Q0. I will say QP. QP is A over B minus. Please note that this I changed the sign like this. This I will call this Q last, QL. Okay? So if I put it here, number 1 times QL times 4 like this, I will put equations like this. I will start with 10 bar plus this is QP times 6 bar equals 4 bar. Okay? I rewrote like this, and here I will let it x0 6 bar, then plus QL times 4 bar equals 2 bar. Do you follow with me? Here please note that I will just put it like this. Okay? So we let x0 here, x naught 1, and y naught QL like this. We will let like this. This is initial value. We will let like this, and we will put it here, x naught here, x naught 1, y naught QL like this. Then it becomes x naught 6 underscore, y naught 4 underscore, then 2 underbar, like this. Now we put this equation here, then it becomes x naught 6 underscore plus y naught here 10 underbar plus QP times 6 underbar equals 2 bar. In this equation, instead of this place, we put this equation, substituted like this. Here, we rearrange. Please note that we have to compare this one with this one. We have to compare. 10 bar comes first. 10 bar comes first, okay? So we rearrange like this. Y naught 10 bar plus, now we rearrange this one, 6 bar, so it becomes x naught plus y naught QP plus then 6 bar equals 2 bar. Okay, this is the next step. If we compare with this equation and this equation, we can find this is x prime, next x, this is y prime, like this. So here I will rearrange. This is the first step. X naught equals 1, y naught equals QL, last one, the last one, and the next x prime equals this is x prime is y naught. Y prime equals x naught plus y naught plus QP like this. Here this x, y naught is actually this one, the previous one, and this x naught is means this one, this previous one. So if we let like this value can be deleted. So we use another step here. We let t equals x, x equals y, like this, and we delete it. We, instead of x, we have to put t here, so it becomes t. And y naught becomes actually previous y, then like this. This is QP. So Q is computed like this. Q computed A over B minus. Q is computed like this. This is extended Euclidean algorithm, and I will make it in C++ code. We will implement this. In code. Here, first, int EEA, it means extended Euclidean algorithm. int A, int B, int reference x, int reference y. Here, we assume that A should be greater than B. Precondition. This is actually important. Precondition A should be greater than B. Here, int R equals A modulo B. If R equals 0, then at this point it means 15x plus 5y equals 5. In this case, 15 modulo 5 is 0. 15 divided by 5 is 0. So it is 0. In this case, x should be 0, y should be 1. Because 15 0 plus 5 1 equals 5. So x should be 0 and y should be 1. And we are returning GCD. So GCD is B. Okay, you should understand this. Next, else. At this point, R is not 0. Here, we first compute G, EEA. We are calling this function again. This is next A should be previous B, as I explained a moment ago, and this should be R and X, Y. Here we compute, I will let it G, uppercase G, int Q should be minus A over B. I explained this before. Here Q should be A over B minus. Here, if x equals 0, means x equals means 0, it reached the bottom. It is calling recursively, it reached the bottom. Then it should be initial condition this. So x equals 1, y equals q. Else, now this step, int t equals x, x equals y, y equals t plus y times q. Now we close the loop here. At this point we close the if statement. Now here, since we return b, we have to return g. Now we close the function. This is extended Euclidean algorithm. Now I move to my computer and I will implement everything. I need to mention another thing. Because we assumed A is greater than B, this is internal representation of extended Euclidean algorithm. I need to make another function here. Here, say int EEA A B X Y like this, the same. Now in the function if here int A1 equals A, B1 equals B, like this. If B1 greater than A1, B1 greater than A1, we have to swap A1, B1. Okay? After this, we call this function int g equal underscore EEA underscore. We are calling this function A1, B1, X, Y, like this. Okay? So at this stage is very important. If, because we swapped here, we have to double check with this one, AB. Okay? So we say A times X plus B times Y is not G, means it's swapped. Okay? Here is swapped. It's swapped, then we have to say swap X, Y. Okay, this step is actually very important. Then we return G. Then the function ends. This is public interface. This function is public interface, and this is internal representation. So this function should not be called directly outside directly. It should be called through this function. Okay? Because and here we assumed A is greater than B. Because and we handle properly like this. And if we have swapped A and B, then we have to swap the result X and Y again. Okay? Now I move to my desktop and implement this algorithm. If we implement extended Euclidean algorithm, then we can get a specific solution of Diophantine equation of this equation. Then we can get general solution. Please note that my algorithm C++ implementation is based on Diophantine equation practical example by DLBmaths, this gentleman's YouTube video, and another one is also the same gentleman but different video. Actually they are very similar, and these two I basically my algorithm is based on these two videos. And another, I would recommend you to watch another video I already filmed, Euclidean Algorithm Theory and Implementation. Also this linear congruence C++ implementation. These two videos, if you cannot understand my current implementation, please watch them. So also while coding, while following with me in C++ implementation, please watch this gentleman's video, Diophantine equation practical example. Okay, I created an empty solution, empty project like this. Here I include IO stream. Now here I will create GCD int A, int B. This is Euclidean algorithm, Euclidean algorithm for GCD, greatest common divisor. I am using loop. If B greater than A, then we have to swap A, B. Okay, so here int R, while R equals A modulo B is not 0, not 0, then here A equals B, B equals R, then here we return B. Utility, and I have the STD here. STD. Okay, that's done. This is Euclidean algorithm. Now I am creating extended Euclidean algorithm. I would name EEA, INTA, INTB, INT reference X, INT reference Y. Here, say AX, A times X plus B times Y equal GCD X Y. Okay, GCD will be returned. GCD A B. Here precondition A should be greater than B. Okay, this is important. Here now INT R equals A modulo B if R equals 0, then X equals 0, Y equals 1, return B. I explained this like this. For example, 15x plus 5y equals 5, for example, then x should be 15, x should be 0 plus 5, 1, 5, right? Then x should be 1, and y should be 1. Okay, that's y. Else here, INT G EEA, extended Euclidean algorithm. Here should be B and R, X, Y. Then INTQ equals minus A over B if X equals 0. It means it reached bottom here. Then we let X 1, Y equals Q. Okay. Else here INT T equals X, X equals Y, and Y equals T plus Y times Q. Okay. Now here we return G. Okay, this is internal representation. Now we are calling this function. This is, I will say, extended Euclidean algorithm, internal representation. Here now we are calling INT EEA, Euclidean algorithm, INTA, INTB, INT reference A, INT reference Y, INT A1 equals A, B1 equals B. If B1 greater than A1, then we have to swap STD, swap A1, B1. Okay. Here. Now we call INTZ equals EEA. We are calling internal representation A1, B1, X, Y. At this point, we have to check A times X, B times Y. It should be equal to G. Not if it is not equal to G, then we have to swap STD as the swap x, y. This step is actually very important. Okay, so now we can return g. This solves something like ax plus by equals gcd a y. It actually returns gcd a b. Okay, so this is called extended Euclidean algorithm. This is public interface. Now we created extended Euclidean algorithm. We can now solve our equation. I would say I will create a function, a struct Diophantine. I will create like this, and it needs int x0 and int. Okay, I will initialize it to. This is initialization. Then I would say b like this, and I will create an operator. See, general solution. I will explain. You will see what I am doing very soon. Okay, then int n equals 0 like this. Then here and return x0 plus b times n like this. I will explain more about this. Okay, here and x equals x0 plus b plus n. We will do something like this. Then here I will define operator std or stream operator and std or stream os constant Diophantine. I would say d. Okay, here std os and dx0, this value, then std show positive, then d b, then times n like this. Okay, then return os. We are actually displaying this Diophantine here. Then let me see. I will create another struct struct dios. It has two solutions, two struct Diophantine. I would say x Diophantine y. This is the structure we defined here. Okay, so here I say bool is failed, means our solution failed. Then I will return like this. If x0 equals 0 and y x0 equals 0, then its solution failed. Okay, so you can test like this. Another thing, now we are solving Diophantine equation ax a times x plus b times y. We are solving Diophantine equation here now equals k. Okay, so it returns dios. We return this structure. You will soon see Diophantine int a, int b, then int k. Okay, now we have to, the very first step is we have to compute the GCD of a and b. Okay, say if I will declare one dios, I will say d. I implement like this, declare. Now if if k modulo d equals 0 means we can solve solutions. Okay, about this, no, this should be g like this. About this I explained in explanation. In this equation, k, this means k should be evenly divisible by GCD AB. Okay, that means k modulo g should be 0 here. Then we can have equation intx y. We solve intz. Actually we don't need g, but I will try it anyway. No problem anyway. And a, b, x, y. I will say g like this. Then here d, x. We are setting the first x. This is x's coefficient. It should be x times k times g like this. Please remember the explanation I have done in video in just a few minutes ago. Then now here d x b should be, if x is greater than 0, for example, then I would let b minus g, it should be g, okay, else b minus g like this. Please think about this carefully. And if x is, it means, okay, I will explain it. If x is less is greater than 0, then let b be negative. Okay, x is greater than 0, then we let b as negative. Okay, so dy x0 is y times k over g. See, this is the same. And here dy b equals, we put we would let dx b, if is greater than 0, then we would let minus a over g. Let me see. Okay, then a over g like this. Here I will give more explanations. If we set x x0 minus b g, I mean here, times x0, okay, this is x0 actually, here bz like this, bz times n, then we set y would be y0 plus a over z times n. If we set x equals x0 plus b over z and here I can make a string like this, then we set y equals y0 minus a over z n. We are setting symbols like this, okay? Signs like this here. Then we solved everything. We set everything, I think. Yes. Now we return d. Okay. Say return d. Okay. So we solved. Now in the function main, int main, we are testing here. And we first try with this video. First one, this one. Then we solve them.
Does that take b?
Please watch this video.
Minus 2 to 5.
So remember this value. 195. So we put here 195x plus 195x plus 42y 42y equals 12. We are solving this equation STD. We say Dios D1. We solve Diophantine. A is 195. B is 42. K is 12. We are solving it as okay. So here we have to say if D like this, D1 is failed, means we have to put like this. Okay. If not failed, then we display stdc out. We can say x equals dx d1x. Okay, std and there like this. Now we put another one. This is y dy. Now now let's see. Now we have to, now let's see. Control F5. Shit. Abort. Let's see what's the problem. I made here stupid mistake. EEA. No. I have to call like this. Let's try it. Let's compare. X equals minus 12 plus 14n. X equals minus 12 plus 14n. Y equals 56 minus 65n. Say the solution is correct. Now I want to fix here one more. Here, then I would say std no show 4. Now I will try again. Okay. Now we will try another one. We will try another one here. I will copy it. We will try another one. I will say 2, 2, 2, 2, 2, and not this example. Here, let's move a little bit here, and they actually got solutions here. We will try it. I will try it. 6, 9, 27, 12, 18. 69, 27, 12, 18. 12, 18. Like this here. 69, 27, 12, 18. Now let's try it. 100. Let's compare with this result. See, this is x term. 812 minus 9 minus 20 30 minus 20 30 plus 28n. So this solution is correct. My solution is correct.
Realizing I can cancel by.
And we can try with someone else's. For example, I will try with this one, this gentleman's. Here I will try this one, not this one, this one. Let's try with this one. 64, 2. Here I will copy once more. I will put std, cout, std, and there. I will copy this, and 6x 64y, 6x 64y, 64y, and 2. So this should be 6, 64, 2, like this. Now try run it. Cancel. It should be 3, 3, 3, 3. This is the solution. Let's compare it. Here, 11 minus 32n plus 32n minus 1 plus 3n minus 3n. The symbol is the sign plus minus actually swapped, different from mine, but my algorithm the result is actually the same as I explained in the theory. As I explained with using board, this plus or minus actually can be swapped. We can test it the result if my solution is correct. For example, I defined operator here. If we put n0, it gives default value. But if we put another one, we can test it like this. We can test my validity like this. If this is 6 times d3x it gives operator, for example, 0 plus 0 means specific solution. Then 64 times d3 y0, for example, equal, it returns GCD. What is this? Equal to, then the solution is correct. My solution is correct. STD, C out, I say correct. Else I can say wrong. I can say incorrect or wrong. Incorrect, I would say incorrect. So let's try it. Control F5. See, correct. Now I try another number here, 1. The next solution, then you can try it. See, correct. So we can try like this also for int 0 I, for example 5 plus plus I. We can display solutions, multiple solutions like this. STD, cout, x, d3 x I, like this. And another solution, this is y, this is y. Then we can display multiple solutions. See, this is the first solution, second solution, third solution, fourth solution, fifth solutions. You can say here, I can say STD, and there. You can say here, STD, cout, I, STD, and there. No, I'll say STD and there. Now try it. See? Give solutions. This is actually first, second, third, fourth, fifth. We can have general solutions. This returns solutions, general solutions. This concludes our Diophantine equations implementation. It's actually pretty easy, I guess. This is GCD. This is Euclidean algorithm. This solves Diophantine equation. This solves Diophantine equation and returns D, and we can access D1, D2 like X, Y component. If we put 0, it returns general. If we put 0, it gives specific solution. For example, when I is 0, it gives a specific solution. When I changes, then we can have next iteration of solutions. Thank you for watching.